Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published just 2 days ago, which introduces a new model that achieves strong performance using drastically less speech data for training, about 23,000 hours compared to 7 million for some other models. This paper is titled Stream-Omni, Simultaneous Multimodal Interactions with Large Language Vision Speech Model. Alright, the core idea here is making multimodal models, models that understand text, images, and speech, much more efficient. Instead of just combining different data types by tacking them onto each other, a process called sequence dimension concatenation, Stream-Omni is more purposeful. For speech, it uses a clever technique called connectionist temporal classification, which is a method for aligning sequences, like matching sounds in an audio stream to written text. This allows the model to learn with far less data and enables some really cool real-time features. Also, the authors shared their implementation on GitHub, and it's pretty comprehensive. You'll find the model code, quick start guides, and even scripts to launch a web demo. It has everything you need to actually run the chatbot and test out those simultaneous multimodal interactions for yourself. On Hugging Face, you'll find the 8 billion parameter model weights and demos showing its simultaneous text, vision, and speech interaction. Alright, so this diagram really gets to the heart of the new architecture. On the left, you see the typical approach, where vision, speech, and text data are just lined up one after another, a process called sequence dimension concatenation. Now, on the right is the Stream-Omni design. It uses a more sophisticated method for speech, called layer dimension mapping, which is powered by connectionist temporal classification. This is a technique for precisely aligning audio with text, and that alignment is what lets the model produce a live transcript while it's still listening. Building on that design, this figure shows the detailed data flow. You can see how speech, text, and vision inputs are handled differently. Speech goes through a speech tokenizer and then into what are called bottom speech layers. This is where the connectionist temporal classification decoder works its magic, generating live automatic speech recognition, or ASR, results. Automatic speech recognition is just the process of converting spoken language into text. These different inputs are then fused and processed by the central large language model to generate the final coherent output. This table then details the 3-stage training process used to build the model. First, they train on vision and text tasks. Then, in stage 2, they focus specifically on speech and text. Here, they use that connectionist temporal classification method to train the model on automatic speech recognition tasks, essentially teaching it to transcribe speech accurately. The final stage brings everything together, training on vision, speech, and text simultaneously. This step-by-step approach is key to how they achieve such strong results with a relatively small amount of speech data. Moving to the results. This table shows how Stream-Omni performs on a whole suite of visual understanding benchmarks. These are basically standardized tests for how well a model can interpret images. And what's really striking is that Stream-Omni, shown on the bottom row, holds its own against many other leading models, even some that are specifically designed for vision tasks. This is a key result, because it shows that adding the speech capability didn't hurt its visual skills. This problem, called modality interference, is a common challenge, but their approach seems to avoid it. Alright, so we've seen it's great with images, but how does it handle speech? This next table dives into that, showing results on spoken question answering benchmarks. These are tests where the model listens to a question and provides an answer, either in text or as speech. And you can see Stream-Omni, on the bottom row, gets the highest average scores for both task types. What's really remarkable is that it achieves this while being trained on significantly less speech data than many of the other models. This really underscores the efficiency of that specialized training approach we talked about. Okay, so now we're looking at a tougher challenge, combining vision and speech. This table shows results on the spoken visit benchmark, which tests how the model handles these mixed inputs. For example, taking a vision plus a speech input to produce a text output. And what you can see is that Stream-Omni, on the bottom, outperforms the other comparable model, Vita 1.5, on these tasks. It's also the only model listed that can take both vision and speech in, and then generate speech as an output. This really highlights its strength in truly integrating different senses. So putting it all together, Stream-Omni offers a really clever approach. The key takeaway is how it moves beyond just stitching different data types together, a process called sequence dimension concatenation. Instead, it uses a more tailored method for speech, that connectionist temporal classification, to map speech directly onto the language model's internal structure. This leads to incredible data efficiency and enables that simultaneous, real-time transcription we saw. It's a great example of smart design. That's all for this week's AI Research Roundup. Thanks for tuning in.